11.35. So here we have methane gas, 28.4 liters of it. The identity of the gas doesn't really matter because if it's under normal conditions, it'll be behaving ideally. So if I had methane or oxygen or whatever, it would give me the same properties. So I'm going to heat this from 35 to 72. I'm going to heat this gas up. The pressure is going to stay constant. So when I heat up a gas, what normally happens to the pressure? Normally it increases, right? Because if I make the molecules move faster, then they collide harder. The pressure is a result of the force of those collisions. So harder collisions normally creates more pressure. So if I don't want the pressure to go up, I want the pressure to be constant, what do I need to do? There's two things I could do when I heat up a gas to keep the pressure from increasing. Right, one would be to increase the volume, right? So if I expand the container, even though the particles are moving faster, they're not colliding with the surface as often because they're spread out more and the collisions on the surface are spread out over a greater area. So since the pressure is really how hard they collide divided by how much space that's spread out over, the pressure won't go up if I spread the force out over a greater amount of area. The other thing I could do would be, right, decrease the number of moles. If I allow some of the gas to escape, then even if I don't change the volume, if I heat up the gas and some of it escapes, then I have fewer particles in there. So the particles I have may be colliding harder, but if I have fewer of them, the net force of those collisions isn't really going to be changing, so the pressure won't change. So conceptually, we have a sense for what's happening, but in this particular problem it says, what's the final volume? So it doesn't say anything about the moles changing, so I guess we have to assume that the vessel holding the gas is sealed and that no gas is going to escape. So that means the moles are also going to be constant. So if I think about the ideal gas law, what I have here here is the gas under one condition at a lower temperature, and then I'm raising the temperature to a higher degree. So I'm making a change here, and I want to know how the volume will change. So really I want to know, I've got V1, I've got the initial volume. I want to know what's the new volume going to be in order to facilitate these faster moving particles without creating a greater force per unit area of the collision. So one thing I can do is I can kind of rearrange this, and what we know is that when I rearrange this, maybe I'll divide both sides by NT. We talked about this. I can solve for R, and what we said was no matter what my conditions are, if I raise the temperature, lower the temperature, change the volume, change the moles or whatever, if I get the pressure, volume, moles, and temperature and I plug them in here, I should get the same value for R every time, right? That's why R is a constant. So that means that the initial pressure, volume, moles, and temperature before this is heated up will be equal to a constant that's equal to the final pressure, volume, moles, and temperature. Right? If I can determine that multiplying and dividing these properties of the gas together gives me a constant, then it should be the same constant that I have when I have the lower temperature that I have when I have the higher temperature. In this case, though, it's not just R that's a constant. The problem is telling me that P and the moles, it's not outright telling me the moles are constant, but I have to assume that. You know, in the exam, I would try to write that outright so you know, and if there's any question about that, just ask me during the test to make sure. If you're assuming something's constant, you can ask me. I can let you know if that's the correct assumption. If those are also constant, then I really want to rearrange the formula to get them on the same side as R. So I have one constant. That will make the math easier for me. So instead of dividing both sides by NT, what I can do is get the pressure, moles, and R all on the same side. So I can divide by the temperature, get that over here. That will cancel here on the right-hand side. And then I can divide by the pressure and get that over here. Since that's constant, get it on the other side with the other constants. That will cancel. So now I have BT equals a constant. Since it's a constant, that means my initial volume and temperature will be equal to the same constant as my final volume and temperature. Oops, temperature 2. So now I've created an equation that I can start plugging into where I have every variable known except one. All right, if I'm going to solve using algebra, I can only have one variable that I'm solving for. All the other things have to be known. So I can start plugging into that. I've got the initial volume, which is 28.4 liters. I've got the initial temperature. So these temperatures need to be in Kelvin, though. So I've got to convert both of my temperatures to Kelvin. So that's 308 Kelvin. And this one, when I add 273.15, going to give me 345 Kelvin. So the initial temperature is 308 Kelvin. The new volume is what I want. The new temperature is 345 Kelvin. Assuming I did that math correctly in my head. So then I just need to multiply both sides by 345 to solve for V2. The kelvins will cancel, and I will have the new volume in liters. 28.4 times 345 divided by 308 gives me 31 3 sig figs 0.8 liters. That's how much the volume will have to expand to accommodate those faster moving particles without creating greater pressure as a result of the force of those collisions. Questions about that? If you hadn't converted these temperatures to Kelvin, you would have got a totally wrong answer. Right? Because the movement and speed of the particles is not proportional to the Celsius temperature. When I go from 35 to 72, that's like a doubling the Celsius temperature. That doesn't mean that the particles are moving twice as fast. The speed of motion of the particles is not proportional to the Celsius temperature. It's proportional to the Kelvin temperature. So the Kelvin temperature goes from 308 to 345. That's not doubling. So the speed of the particles is not doubling. It's only a slight fractional increase, which is why I see a slight fractional increase in the volume from 28 to about 32. It's a proportional increase. The factor that the temperature is increasing by is the same factor that the volume is increasing by. That's Charles' law.